Good
evening, everyone, and welcome. My name is Mark Adams. I'm in charge of education and public outreach at the National Radio Astronomy Observatory, and we're delighted that you all were able to join us tonight for the 40th Annual Jansky Lecture. To begin our program, we'll show a brief, about a 3-minute video that provides an overview of the observatory's mission and science. And immediately after the video, Observatory Director Fred Lowe will introduce our distinguished speaker and his Jansky lecture. So we'll do the video now. We think we've defeated the demons of technology.
Whether exploring the origin of our own planet or detecting the faint afterglow of the Big Bang, astronomy helps us answer some of the most exciting and fundamental questions about our universe. Helping to extend our vision deeper into space and our understanding further back in time is the National Radio Astronomy Observatory, a premier research facility of the National Science Foundation and operated by Associated Universities Incorporated. Today, astronomers and students throughout the world use NRAO's instruments to open a whole new window on the universe. By studying the light in the form of faint radio waves from distant stars and galaxies, astronomers learn critical, often breathtaking information about these distant objects, and even about the origin of life in the cosmos. The NRAO enables astronomers to make these stunning breakthroughs by designing, building, and operating the most powerful and advanced radio astronomy telescopes in the world. Using these highly sensitive instruments, which detect radio waves of the meter, centimeter, and even millimeter wavelengths, astronomers can identify the molecules in space and are able to peer through immense clouds of interstellar dust and gas to unveil stunning objects, such as the center of our own Milky Way galaxy. NRAO telescopes provide state-of-the-art resources for astronomers and students to help advance our understanding of the cosmos. The Green Bank Telescope in West Virginia, the Very Large Array in New Mexico, the Very Long Baseline Array stretching from the Virgin Islands to Hawaii, and the highly anticipated ALMA facility in Chile ensure that radio astronomy will remain a vital component in expanding our understanding of the cosmos. Indeed, of the 10 Nobel Prizes awarded for astronomy, 6 have been based on research conducted by radio telescopes. We are now on the threshold of even greater discoveries. With its efforts to expand and enhance the VLA and ALMA's ability to see all the way back to cosmic dawn, NRAO will continue to expand the boundaries of our scientific knowledge and help us to unlock the mysteries of the universe.
I hope you enjoyed this brief overview of the observatory's mission and science. Now it's my great pleasure to introduce Dr. Fred Lowe, the director of the National Radio Astronomy Observatory.
Good evening, everyone, and welcome to the 40th Annual Jansky Lecture. This distinguished lecture series was established by the Observatory's parent organization, the Associated Universities Incorporated, to honor astronomer or astrophysicist who has made significant contribution to astronomy, and to honor Carl Jansky, who in 1932 detected the first cosmic radio waves, and therefore leading to the science of radio astronomy. And it's a special pleasure to welcome Carl Jansky's son David and his nephew Curtis Jansky to the lecture. But today we're especially pleased to have Professor Rashid Sunyaev as a 2005 Jansky lecturer. Professor Sunyaev is a director at the Max-Planck Institute for Astrophysics in Garching, Germany, and he's also the chief scientist of the Space Research Institute of the Russian Academy of Sciences. He was educated at the Moscow Institute of Physics and Technology and received scientific degrees from Moscow University. He's one of the most important and prolific members of the Moscow group that pioneered many branches of relativistic astrophysics and cosmology. Together with his mentor and long-term collaborator of another distinguished Russian astrophysicist, Yakov Seldovich, they study important physical processes in the early universe, including the recombination of hydrogen and the formation of the cosmic microwave background radiation. They predicted the recently discovered acoustic peaks in the microwave background radiation and the decrement in this radiation that is due to the scattering of the microwave background by the hot gas in galaxy clusters, the so-called Sunyaev and Seldovich effect. As you may know, in the last 5 to 10 years, a series of very precise experiments made a lot of measurements of the microwave background and led to very important advances in our understanding of the universe. And most of that advance was based largely on the seminal work of Professor Sunyaev and Seldovich. Professor Sunyaev is also very much involved in the space program in Russia, having a lot to do with the various experiments like the Granat, the Integro, and he's also co-eye in the upcoming very important experiment, Planck, European mission, also designed to study the microwave background. Professor Sunyaev is a member of the Russian Academy of Sciences and a foreign associate of the National Academy of the Sciences in the US and the American Academy of Arts and Sciences. And he has received numerous awards for his work, including the 2003 Heinemann Prize of the American Astronomical Society, the 2000 Bruce Medal of the Astronomical Society of the Pacific, the Gold Medal of the Royal Astronomical Society, and the Bruno Rossi Prize for significant contributions to high-energy astrophysics. Without further ado, let's welcome Professor Sunyaev, who will tell us about the cosmic microwave background radiation, clusters of galaxies, and cosmology.
Thank you. I have.
Oh, you have? No. Oh, you need another?
I need both?
Yes.
Okay.
We don't want to miss anything you say.
Yes, thank you. Now I'm heavily loaded. It is great pleasure for me to be here. First, because name of Karl Jansky is holy for practically every, for practically every astronomer in the world, because this is I was student, and at that time, first time I met name of Karl Jansky, not because he discovered the radio waves from space, but because there is a great unit, Jansky, which was introduced in this connection, in this beautiful physical unit, and in reality, today, here at NRAO, radio astronomers are observing objects which are sending us flags on the level of micro-Jansky and even nano-Jansky. I will speak today about world which is much more distant than majority of galaxies on this beautiful picture obtained by Hubble Space Telescope. In reality, I will speak about processes which occurred in the universe when our universe was tens of thousands times younger than today. And what is important, the traces of these very interesting processes are on our sky. And what is even more important, we are living in a very special moment. These traces will be practically the same next 3-5 billion years. And therefore, it's very fundamental what radio astronomers today are doing, and a lot of effort there. People in different countries are trying to get new information. There is very strong competition who will be first. And this is very important, and I think that you should all know about this. I prepared, when I was coming here, I thought that I will be speaking in National Radio Astronomy Observatory, which is key scientific center of the world. And I prepared very, how to say, sophisticated talk with a lot of formulas and so on, and many, many new things. But my colleagues here 2 days ago used, I don't know how to say, a volume of very cold water. They told me that I should completely change my talk and it should be very, very simple. May I apologize, it will be, I am unable to give extremely simple talks, therefore I will show several introductory slides, just short introduction, and then I will try to give you scientific talk, which I think is understandable for undergraduate students. Okay, I will be using during this talk many times, okay. I will be using many times what redshift. And I think that majority of you know this, what it's connected only with Doppler effect. And if object is moving from us, then the wavelength is becoming of any photon is becoming longer. And if object is coming towards us, thank you, then this wavelength is decreasing. Astronomers are using very good redshift, and this is Z, which is observed wavelengths, and the wavelengths which we are measuring in the labs, which is really properties of the different atoms. Therefore, you see that -1. This will be redshift, and I will be speaking about it many times. And people are observing today, every astronomer is using this redshift practically every day, many, many times. But before, in the beginning of century, practically people were not thinking that this redshift determination will be so important. But Edwin Hubble was first person who, on this great telescope on Mount Wilson near Pasadena, California, 100-inch telescope, which today is considered as a rather small telescope. We have much, much bigger. But at that time, this was the biggest telescope in the world. And Hubble found that if objects are weaker and weaker, then their velocity is increasing. And they all are recessing. And this was proof, in reality, there were several people, Alexander Friedman in Hungary, St. Petersburg, just after Russian Revolution, found the equations which showed that our universe cannot be static. It should expand or should collapse. And Einstein was a referee of this paper, and he gave negative report. In the beginning, he told it is impossible. But after several exchange of letters, and I think in 1920s, in the beginning of 1920s, letters were going to Russia very slowly, Einstein agreed that this is absolutely correct mathematical result. And paper was published. Simultaneously, Lemaitre in Brussels found similar solution. And only 7 or 8 years later, Edwin Hubble proved that universe is behaving exactly as this simple mathematical solution is predicting. Therefore, we know that universe is expanding now. Again, for people who are not astronomers here, it's interesting to see, I like this picture, which shows you how universe expands. Look, at some moment, distance was very small, and then the same distance is increasing. But if these are galaxies, all distances between all galaxies are increasing in the same way. And this is the expansion, not that expansion is coming from one point, but each point is going out from another point. And this is how our universe is expanding. I will speak today also a lot about the past of the universe. If universe is expanding, then Previously, its density was much, much higher. It's impossible to say that it was small. If universe was infinitely large, it was infinitely large even at that time. But what is important, that density of matter, and especially temperature, was changing with time. And you see, I will speak about time in reality. Today I will be speaking only about times which are exceeding 380,000 years. But look, it was practically impossible to see anything before this time because universe was optically thick. Photons were unable to come to us. But at this moment, the recombination occurred and universe became transparent. We can see this surface, and this is last scattering surface. And I remember how I was writing formulae of recombination, found vanities, and it is unbelievable that it was possible to find in 1969 position of this surface, and today with precision, delta Z, better than it is at 1100, redshift 1100, and delta Z is absolutely the same today. It is WMAP proved that it's practically the same place. And you see then universe became optically thin, but due to gravity, gravitational instabilities were slowly growing, in the matter were slowly growing. We do not see anything here, and after time, about 2 million years, 5 million years, first galaxies, first stars appeared, and here, today we know that it's 13.7 billion years. It's very precise. See, we know this. I will tell how people found this, but we know now our age with very high precision, and this is redshift 0. But when we go in this direction, redshift is increasing, and this place corresponds to redshift 1100. First stars appeared, we don't know exactly when. Today it's one of the main goals to find when first stars appeared in the universe, but it seems that they appeared at the redshift between 6 and 20, where we know again from many measurements where reionization of the universe occurred. This I'm giving you the correspondence that there is redshift Z today, redshift is 0, and this is our age. And you see, if I'm speaking about early universe, this high redshift. I will be speaking a lot about 1100, about 620, and 2-3 redshifts. And you see corresponding time. Here, 380,000 years, when the universe was so young. There were, I told already about Hubble, but there were other people who were absolutely great and who changed our life. One person was George Gamow. He born in Odessa, in Ukraine now, and whole life he was working in when he was young, he was working in St. Petersburg, and he made beautiful results there. He was first who explained how the alpha decay, nobody was understanding how alpha decay of nuclei is going, and he first told about that there is a probability that some particles due to quantum mechanical effects can go through the barrier, and this was solution of George Gamow. He was very, very young at that time. Then he was able to leave Soviet Union. Stalin was unbelievably angry with this, but then he was in United States, and he was working in United States, and in around 50, he and a group of young people around him, they predicted that in the universe there should be radiation, uniform radiation with temperature of the order of 6 Kelvin. Gamow wanted to make all chemical elements in the very early universe when densities were very high, and if temperature is high, it is possible to have nuclear reactions. He wanted to get even uranium at that time. This was incorrect, but we know today that practically all helium, all deuterium, practically all lithium in the world are produced during first, second, or maybe first minute of the life of the universe. And this part is going exactly according to scenarios of George Gamow, how he predicted very, very long ago. But he predicted also that there should be radiation, and he estimated temperature of this radiation 6 Kelvin. It was impossible to measure because, as you know, discovery of Carl Jansky that there are cosmic sources of radiation was very fresh, and there were no real instruments to measure this. But in 1965, already Nobel Prize was given to people, to Arno Penzias of Bell Labs and Robert Wilson. They discovered that their dish had unpredicted, they didn't knew about result of Gamow. It was very good dish for telecommunications, and they thought that noise of this dish will be very, very low, but dish had noise. And then, with some help of people from Princeton, people recognized that this is just radiation which is coming from our universe, and temperature of this radiation is 2.7 Kelvin. Very, very low temperature, but it's everywhere. But because universe is expanding, it's immediately, we all know, if we compress the universe back, then temperature would be high. And temperature was so high that nuclear reactions were possible in the universe. This is absolutely great result, but even today, 400 photons in every cubic centimeter of the universe, everywhere in whole volume of universe, are present due to this radiation. And for me, it's very important that there were people who predicted this before it was possible to observe and before we had the technique to observe this. People during next practically 20 years were trying to detect any inhomogeneities of this radiation because radiation was practically isotropic and has a best black body spectrum. It was like, it's unbelievable that people till now are unable to detect any deviation of the spectrum from black body. We certainly know that there are these deviations, and I'm sure that in 10 years, somebody of young people who are in the room will observe it, and we will find and we will understand a lot about physical processes in our universe. These are beautiful processes. Decay of dark matter, decay of primordial turbulence, first shock waves in the universe. We can find annihilation of positrons. We can understand many things just studying spectrum. But people are especially successful now to measure angular fluctuations. And Wilkinson MAP spacecraft is made really great contribution. I was invited by Princeton group to launch of this beautiful spacecraft, and I was staying together with David Wilkinson. I'm happy that he saw first results from his child, from this spacecraft, but he died several, I think half a year later, and it was already when he knew that all instruments are working properly. And this great spacecraft. And you see, temperature of sky is 2.7 Kelvin. And here, maximal deviations are dark blue, minus 200 microkelvin. They are 10 power 5 times smaller. And red, these are the brightest spots. They are only 200 microkelvin brighter than average temperature. This is unbelievable sensitivity. And people are measuring now, today, WMAP is able to measure these deviations with precision of the order of 1%. But theorists who are working further can tell you we need precision of these measurements to be increased at least 10 in power 4 times. Then there will be a lot of new beautiful effects. And it's necessary to measure polarization, and then we understand how first inflationary processes were working in the universe. Without this precision, it will be very difficult to measure these things. And people are working, and many people here are smiling, but I can tell you, I know very serious experimentalists in Princeton, at Caltech, and in in NRAO who are thinking how it is possible to do. And I'm sure that time will come. Okay, let's go further. Again, how these fluctuations, why we see these fluctuations. There was last scattering surface, and we see this surface, how all photons from here are coming directly to us, and we can observe them. And it's very, very important that any inhomogeneities which were existing here, universe just at some moment became transparent. You are sitting in the evening in the room, and there is light, but fences are closed. And you are opening, and people from outside can see immediately what is inside. It is the same. Everything was non-transparent, and then it became transparent at some moment, in very short moment, and you can see everything. I will speak in this connection about acoustic peaks. May I apologize, it's a little more complicated, but I see here many professionals. And situation is the following. This picture from paper written in 1969. And you see, this is a scale. Just you're taking object, dimension of the universe containing given mass divided to solar masses. And this is 10 to the power 5 solar masses, 10 to the power 10 solar masses, and 10 to the power 15 solar masses. And this is 1 solar mass. And it's very interesting. When universe was expanding, in the beginning, all these objects were much bigger than horizon of the universe. It was impossible to send signal from one place to another, and therefore people are speaking about inflation. But due to gravity was existing, and therefore all perturbations here were growing. And they were growing, you see here, as power law. But then they crossed the horizon of the universe, and universe became equal to that object, to 1 solar mass, to 10 to the power 5 solar masses, to 10 to the power 15 solar masses. At this moment, liquid consisting of radiation, mainly, radiation has unbelievable pressure. And this liquid behave according to all physical laws. And physical laws are showing that it's possible only to have acoustic waves here. And amplitude of acoustic waves was proportional to amplitude of these inhomogeneities of mass there, and wavelengths was dependent on the scale. If mass is bigger, wavelengths also of these acoustic waves was longer. And these acoustic waves were going in the universe everywhere, and these were standing acoustic waves, and then recombination occurred. And they came, all these acoustic waves, with different phases to this place. Somewhere you had minimum, somewhere you had maximum. And due to this, as a result, it was possible to have also some modulation depending on the scale of the mass. After that, matter dominates in the pressure, and again, we had the growth of perturbation. This was prediction. In this theory, dark matter was absent, but dark matter is practically confirming this, is making only more beautiful these results. And what we have finally, you see this is modulation. Today, amplitude of fluctuations of matter, and it depends on the mass or on angular scale. Most important here, that these dimensions depend only on crucial parameters of the universe, Hubble constant, how universe expands, and on, physical constants, and on temperature of CMB. Therefore, we know how to compute at any time what is the distance between these peaks. And this is most important thing. After recombination, we can measure it at the moment of, on the last scattering surface at redshift 1100. But now Sloan Digital Sky Survey observes these baryonic wiggles in the distribution of elliptical galaxies and is able to see them very, very close to us. They are existing. Even it was when universe, originated when universe was very, very young. And look what is observed. These are beautiful data from WMAP, and then from small radio telescope like CBI in Chile, where ALMA will be working, Akbar, this is South Pole. People are coming to the South Pole to work there to observe these wiggles, and you see the results. People see them really and just measure, and you see error bars are very, very small. I told you about 1% precision. And this was dream for 30 years. Nobody was able to detect these things. Now we are measuring them with 1% precision. And what is important, that characteristic position of this maxima and minima is immediately giving us practically all key parameters of our universe. We know what is its age, what is the density. We know that matter will consist of baryons, of normal atoms, normal matter, and that this matter contributes tiny, few percent to the matter density in the universe. There is dark matter. Nobody knows what is dark matter, but we're sure it is there. And there is dark energy. Nobody even understands what it might be, but it is there, we are sure, because we are observing this. It is necessary to continue our observations, and we will know more and more about this matter which is absent, which we cannot measure in our labs, because our labs are too small for this, or we cannot get on our accelerators so high energy. I will tell you a few words about how the universe is evolving, how it is, which objects are appearing first, and so on. I do not have time for this, but fortunately, I can inform you that today computers, using the parameters of the universe on the basis of these observations, they are able to model the observed universe, and what is the result of these simulations is unbelievably good, because people can see easily, people can see how that picture which they are obtaining finally is practically the same. What is it? Oh. Look how the structure of the universe is growing. In the beginning, there were no practically perturbations. And you see this is a scale altogether 50 megaparsec. And look how the inhomogeneities are growing, growing, growing. Here, giant cluster, very rich cluster of galaxies will appear. And this will be, today we will see here thousands of galaxies in one place. And you see this is a structure, and this is at redshift 0 today, this is the prediction. And practically the same is observed in the real universe. Observations are showing us that this is correct picture. Okay, I think that I will close this, and I will show you the picture which we see today. This is the picture which is produced in Garching in Germany by Volker Springel, and this is biggest simulation in the world. You see huge dimension, and this is picture of the universe today. And you see these clusters of galaxies are everywhere. And how, you see, smaller dimension, and this structure is, I will speak today about these clusters of galaxies. Look how giant is it, and how new matter is coming from all sides. And we are observing these clusters in all spectral bands. They are unbelievably bright. This is the most expensive simulation for astrophysics ever done. Millennium Run. Max-Planck Gesellschaft in Germany paid for it. And you see, it's beautiful. Look, because everybody is interested. What is our universe? And you see again, and we came, whole universe is 10 gigaparsec. this 1 gigaparsec. And you see on average, it's very, very uniform, very, very uniform. But in reality, you saw that there are clusters of galaxies, there are galaxies. Now people are simulating further, there are stars, around stars are planets, and somewhere on one planet we are living. But this is our world. I will return to more. Okay. This is his first simulation of Volker Springel. And I told you about clusters of galaxies. You saw the simulation with billions of particles. And here is a real cluster of galaxies, which is observed by Hubble Space Telescope. And you see these galaxies. There are thousands of galaxies. They belong to this cluster of galaxies. But these objects, these are galaxies which are very, very far behind this cluster. But huge gravitational potential of cluster of galaxies plays role of gravitational lens and amplifies these galaxies. And we see them this is great because these galaxies are amplified twice, by optical telescope and by gravitational lens. And therefore we can see much, much farther. But this is picture in the optical light. But these rich clusters of galaxies contain not only thousands of galaxies, they contain also very hot intergalactic gas, and temperature of this gas, 310 keV. We need such temperature on the ground so that fusion reactions will be possible to get energy from deuterium and helium-3, which were synthesized in first minute of the universe. This is the only way for us to get really huge source of energy supply. And people are, you know, that there are plans to build international tokamak reactor in France now. Yes, but it's very important that we also measuring here the dark matter. And motion of this, Fritz Zwicky was first person who I think in 1936, he was measuring the velocities of individual galaxies in cluster of galaxies, and then was trying to find what is the mass. And he found that mass is 30, 40 times higher than the mass of individual galaxies in the cluster. And he told that there should be missing mass. And today we know that it's the same dark matter which is present everywhere in the universe. Yes, I will go to the next. These are the data coming from Chandra spacecraft in the United States, and this is XMM Newton European spacecraft. And you see one of the most nearby clusters of galaxies, Coma cluster, and temperature there is 100 million Kelvin, but electron density is negligible, 3 times 10 power minus 3 per centimeter cube. And we see just free emission of this gas. Since it is so much gas there that clusters are very bright X-ray sources. But now I will return to the time when nobody was able to measure what is the temperature of X-rays there, and nobody was able to prove that this is thermal gas. And I was a very young student, and I am glad that I see some amount of students here. And my advisor, Zeldovich, told me you should find a way to prove is this radiation thermal or non-thermal. He told me, and I began to think what is and how, and it was obvious that the main process here was process of scattering. Normal Thomson scattering of CMB was just discovered, and I thought that if there is photon of CMB and it's scattering and going in this direction, maybe I can detect absorption by this cloud. But when I integrated, I discovered that because CMB is isotropic, another photon which is coming from different direction will be scattered to me, and I never will be able to see this cluster. I came to Zeldovich and told him so, and Zeldovich answered me, oh, this is Tyndall effect, and people know this 200 years. I thought, okay, and I asked what to do further. He told, think, look for the changes of energy, and so on. And then in this, his words that maybe energy changes somewhere were crucial. We were able to think about the change of energy of photon due to the scattering by Maxwellian electrons in the hot gas. And what is important that it's very easy, every student or schoolboy or schoolgirl can immediately recognize that due to Doppler effect on moving electrons, just the same as Doppler effect for moving galaxies, we can find what is the velocities of these electrons, their thermal velocities, and their 1/7 of velocity of light. These huge velocities, they're moving there. And because they're moving with so large velocities, when they scatter, there is Doppler shift of the photons. And today, it's easy to speak about laser light scattered in plasma cloud. If this laser line, after scattering, I have this profile of the scattered line. This, look here, right wing is not much, but stronger than the left wing. This effect of relativistic correction, just special theory of relativity, because velocity is 1/7 of the light. But it is very important for me that this energy is higher. It is the same as average photon is moving towards higher energies. It's very interesting that 10 years after we wrote with Ildovich this paper, people discovered this and used it for tokamak. And for maybe 5 years after 1975, this was the key method to measure temperature of the ground-based tokamak reactors. But, you know, universe is doing absolutely the same. And if you have this for laser line, I can consider now black body radiation, CMB, cosmic microwave background. This is the spectrum of cosmic microwave background. Usually, physicists are telling, oh, it is possible to consider that this is a lot of delta functions, a lot of laser lines, but altogether they are giving black body spectrum. Each line is moving toward higher energies, you see here, and as a result, we are getting resulting spectrum. Total spectrum of CMBs should be shifted, and you see in NRAO Jansky part of spectrum at 10 centimeters, 1 centimeter, 3 millimeter, brightness is decreasing, but in millimeter band and sub-millimeter, there is increase of the brightness. This was prediction. And we were very happy with this prediction. And we're giving this formula, you see, decrease of the brightness, negative flux. Where there is hot gas, we should see negative flux of the decrease of brightness, and positive flux simultaneously at higher frequencies or at lower wavelengths. This was the prediction, and we were very proud by this prediction, but 20 years, nobody was able to detect this. This was much below sensitivity. I know that many people were trying, and I see one person who was trying to do this in NRAO, but this was very, very difficult job. Finally, people found, but this took a lot of time. Main prediction here was that, which is absolutely unusual, if you are observing galaxy, its spectrum depends on the redshift, because all lines are shifted. Here, the spectrum, this spectrum, doesn't depend on redshift. Absolutely. Depends only, doesn't matter at which redshift it's clustered, spectrum is the same, it doesn't depend on redshift Z. People were not believing this in the beginning. Today, it is proved, I will show you. And then some revolution occurred, and everybody began practically observe this effect. It became easy. I think that most successful is John Karlstrom from University of Chicago, and he observed, now he has collection of the order of 100 clusters. I asked John, why you are not publishing every information about every cluster? Answer of John was the following. Each cluster, to process all data, to publish, and so on, this one PhD, where I will find 100 PhD students, you understand me? But Nevertheless, he published this data, and this is interferometer which he used to observe these clusters. And what is possible to prove today? There are very interesting things that if you're observing in X-rays or in optical light, the brightness is decreasing as very strong power of redshift. But this brightness of this cluster doesn't depend on redshift. Therefore, cluster at redshift, for example, 0.888, these are very distant clusters, are as bright as nearby clusters at redshift 0.17. And this was also as it was predicted. And therefore, we can observe clusters in the whole universe. Doesn't matter at which redshift they are. Question, do they exist or not there? And this is today this unique way to measure, to look for clusters, most distant clusters, and to prove when our large-scale structure of the universe was formed, and does it the same as is predicted by these huge and most expensive simulations. Now I show you the picture of photo of my late mentor and advisor, Yakov Zeldovich. You see here in Russia, these were like, now we all are proud that our colleague, Martin Rees, is now Lord Martin Rees. Yes, therefore Zeldovich, this was like to become Lord in Soviet Union, because these are 3 stars of hero. It was very, very difficult to get even 1 star. He had 3. There were several people in the country for the whole history who got this, but all of them were connected with atomic weapon. He got for this, for a completely different part of his work. But I was very lucky because I was working with him, and I came to him as a student who was interested only in elementary particles physics in spring of '65. But when he asked me, do you like to do astronomy? And before, yes, I had conversation that I wish to go to Zeldovich with chair of department where I was student, and this chair told me, what are you doing? He decided he's crazy. Now he has all his stars, and he decided to do astronomy, this useless science, and think about yourself. But I went to Zeldovich, told him, when he told me, let's do astronomy, I told, no, I disagree, it's useless science, and I wish to do elementary theory of fields. And Zeldovich told me, okay, please help me with one problem, and then we will work in theory of fields. I will find for you another problem, but I need some help. And I worked with him on that paper, and never more I was thinking about the theory of fields, because it was so great to work with him. And in reality, when I was great, I think that people who were telling me, they were completely right. Because in early 60s, and this was, I was going to Zeldovich, this was not easy, everything began in '64. Early 60s were not so interesting time for astronomers. There was no CMB at all, no. And there were no black holes, stellar mass black holes or supermassive black holes in the nuclei of galaxies. No, just in '65 already were quasars, but in '63 they were absent. No gamma ray burst. Even neutron stars, pulsars, millisecond and millisecond pulsars, you are working a lot with them. X-ray bursters, magnetars were not existing yet. Nobody knew even about their existence. Life was completely different, and people were doing the same, but life changed. And I remember one conversation with really great mathematician Vladimir Arnold. He's one of the greatest mathematicians of the world. And Vladimir Arnold told me that he was reading carefully letters of Newton and people who were living and doing mathematics before him. And he believes that at that time, it was very easy to make discoveries because nothing was known. Everything what they were doing first. Nobody was doing the same before. I told him, Newton is giant. Don't think that he was bigger than anybody around. He told, no, there are many Newtons around. But today it is much more difficult to do something new because so much is done already. It's necessary to learn before. I told you that I do not believe fully in this. I still think that Newton is absolutely great. But there is an analogy. And I see to this room, I see many people whom I know for many years, who are of the same age as I and who are younger. I can tell you, we all came to the world on astrophysics in the right time. There were nobody knew about these objects, and we were lucky. It was possible to discover them. It was possible to study them in detail. People are now trying to count clusters of galaxies using these effects, which I told you about. And I'm showing you just extreme pictures that if people will count them at clusters at different redshifts, 0, 1, 2, 3, you see different universe consisting only of baryons will predict such distribution and existence of clusters of galaxies only at very low redshifts. When I came to Garching, Simon White was giving talk, and he completely believed at that time that universe is baryonic, and omega is equal 1. He told clusters are existing only up to redshift 0.3. I told, no. I know many clusters which have higher redshift. Something is wrong. This is a universe which consists of matter only, and omega is 0.3. Its universe is open. And this is universe with dark energy and dark matter. This is prediction. And you see these predictions are drastically different. If we only count these clusters of galaxies, we can distinguish immediately, is there dark matter, is there dark energy or not? And this is very, very important. And now we are thinking how to find hundreds of thousands of clusters of galaxies on the whole sky. There are many experimental plans, and people are working, not only radio astronomers, X-ray astronomers, optical astronomers, infrared astronomers. They all thinking how to use this information about clusters of galaxies. In radio, there are several specially designed experiments. First, mirror apex, 12-meter dish, and array of 300 bolometers are already in operation. Bolometers are not there yet. And this is collaboration between Max-Planck in Bonn, Institute of Karl Manton, and University of California, Berkeley. Berkeley is supplying this array of 300 bolometers for this. John Karlstrom is leading South Pole Telescope array of 1,000 bolometers. They will discover up to 20,000 clusters. We all believe that a lot of data will come from Atacama Cosmology Telescope. This is a consortium of East Coast universities led by Lyman Page from Princeton. There is AMI in Cambridge, Amoeba in Taiwan. Many people are thinking what to do, and they're going to the best sites in the world where noise is very small. For example, this is Atacama Desert in Chile, where ALMA will be, 5 kilometers altitude. And South Pole, you know, also is not most pleasant place to live, but it's a great place to do sub-millimeter astronomy. I will show you Cambridge. For radio astronomers, this may be worst place. No, nevertheless, AMI began to work at Cavendish Lab, and you see first picture of the cluster of galaxies, Abel 1914, and this beautiful result, you see they found 8.61 millijansky. This is millijansky flux, negative flux from this cluster of galaxy, and the noise of the beam is 0.19 millijansky per beam. Now you understand that the name of Jansky, radio astronomers are using every day because it's the most important unit. And you see this thing, but for me as for physicists, much more interesting this picture, because they were able to prove with their detector from 13 gigahertz up to 18 gigahertz, you see several channels, that the spectrum of negative object has relay gene slope. It's exactly relay genes. And this is as predicted. And therefore, they show that these are not radio sources, no fluctuations, this is something real, what was predicted. And this is very good and interesting. Now I will speak, I still have some time. I will speak about the possibilities to measure velocities of these very, very distant clusters of galaxies relative to CMB. And most important for us, and you all remember theories in the 100 years ago, people were discussing are we moving against this sphere or not. And today, we know that we have really only one reference frame where CMB is isotropic. And then motion of the solar system leads to the dipole component in the CMB brightness distribution over the sky. Sky is 0.1% brighter in the direction of our motion. This is our velocity, and is less bright in opposite direction. This is the brightest anisotropy of CMB sky, 1,000 times brighter than primordial fluctuations, and this is today main calibrator for CMB experiments. You see the picture, this is a dipole in the picture, for example, of WMAP. It's possible to measure this velocity. But scattering in the clusters of galaxies permit us to measure velocity of every cluster of galaxies relative to CMB at that place. For example, if cluster is moving from us with velocity 3,000 kilometers, or towards us with velocity 3,000 kilometers per second, spectrum is this. If this is at rest, if it is at rest relative to CMB, it is this. And if it is moving from us, we see this spectrum. It's possible to measure velocity. What people are doing, it is very difficult, but Sarah Church in Stanford University and SUSY collaboration, mainly Berkeley, they were able to measure the velocities, and they found that peculiar velocity is 415 plus 920 minus 765. Error bars are much bigger than velocity. And Sarah was very unhappy. She told during conference in Japan that she spent 10 years of her life because theoreticians were telling that peculiar velocity is of the order of 1,000 kilometers per second. Now, theoreticians are telling that velocity is only 400 or 600 kilometers, and it's necessary to walk further. I told her that it's not so important what theoreticians are telling. More important is the experimental information. For example, this group is able to measure same velocity for cluster at redshift 0.8. Precision is practically the same, but this cluster is moving from us due to the expansion, Hubble expansion of the universe with velocity 54% of velocity of light. This is 160,000 kilometers per second. And SUSY observations show that this peculiar velocity is less than 1,000 kilometers per second with respect to the reference frame in which CMB was isotropic. And this is unbelievable. We can show that even there our universe is expanding as we think. Majority of people in astronomy today believe all this, what is written in the textbooks as this Holy Bible, everything is correct. I am telling you that even Holy Bible needs confirmations. And it's very, very important confirmation that everything is close to what we are thinking. Now, next step will be the measurements of internal motions in the clusters of galaxies and turbulence in clusters of galaxies. I will show you now again simulations, what people are doing, how two galaxies are merging. And it is very interesting that we see such pictures on the sky, just there existing, but in addition, it is very easy now to compute this on the same supercomputers which are showing us how the large-scale structure of the universe is growing. I remember how difficult it was in 1970. We were computing this on very old Russian machine, and it was really disaster. And Brother Stumre did this simultaneously at MIT and Boulder. Today, this is just great industry because computers can do everything. I will show you movie, beautiful movie, I think, from which you can see that there are great effects which we can maybe observe very soon. Oh, this one galaxy is going. You see, it's rotating, everything is possible to model. And there's another coming. And look what is occurring, just due to the tidal interaction. And this again, Volker Springel. And I remember how when we got this, we thought, oh, these are beautiful spirals. And look, but a lot of turbulence, a lot of internal motions. And what will occur if two giant clusters of galaxies will merge? I think that picture will be even more impressive. And therefore, we are looking now the ways to measure, to look for internal velocities in clusters of galaxies. And people are making simulations, and their simulations are confirming that turbulent pressure in clusters of galaxies contributes up to 15% of the total pressure of the gas. RMS velocity, therefore, should be of the order of 0.4 of velocity of sound. This is great prediction. And this velocity should be of the order of 300-400 kilometers per second, when velocities of dark matter particles should be of the order of 1700 kilometers in the same cluster of galaxies. There were two ways to measure, and we were thinking that everything will be solved very soon. One is Planck. We thought that CMB will give us a lot of information, but much more interesting was the project between Japanese Institute of Space Research and Goddard Space Flight Center of NASA. They were thinking how to observe Doppler-shifted and broadened X-ray lines of iron. And this was a great experiment because first time this spacecraft was carrying X-ray bolometers. Here are radio astronomers. They know that there are bolometers, and when plenty of small photons, low energy photons, radio or sub-millimeter, they're hitting bolometer, and we can measure what is the temperature. Here people produce a device where one X-ray photon is coming, it's carrying a lot of energy, and it hits bolometer. And it's possible to measure, not only count X-ray photons, but also measure with very high precision its energy. And this is today best way to measure, to make spectroscopy in X-rays. For 6.7 keV line, resolution is 5 electron volts. No one other X-ray spectrometer in space can do this for these energies. This was prediction, spacecraft was launched, and this device was giving, we have information that resolution was confirmed 6 electron volts at least. And Japanese are very careful when they're telling 6 eV, it's much better. It was very, very important for us because it is, I will tell several words now, very simple, because thermal velocity of iron nuclei in plasma is 7.5 times smaller than sound velocity, because these nuclei are very heavy and they're moving more slow than hydrogen. And therefore, this velocity, which I told you about 0.4 velocity of sound, is becoming supersonic for iron nuclei. And it's interesting that Astro 2 was able to measure these velocities, and we were very, very happy with this and expecting a lot of things. These were the predictions. If there is iron line, you see it. This is thermal broadening, and this is turbulent broadening predicted. When we took Kolmogorov spectrum with very big eddies, this was the spectrum which we got. It's very far from thermal broadening and very far from Gaussian with turbulent dispersion. This was a prediction. There are many X-ray lines. You see what we were waiting, expecting, but tragedy. When people are doing space experiments, their life is much, much more complicated than a life of people who are doing ground-based experiments. Because if something is wrong or failure, you can come, take the screwdriver, and change part of the device. I know that life is more complicated, but in space, this is completely impossible to repair. Only Hubble was repaired several times, but you know the debates around now, how expensive it is. But for Suzaku, for this Japanese spacecraft, it is absolutely impossible. And what occurred, that they, after several weeks of work, they lost all helium. In few minutes, all helium from cooling tank evaporated, and they are unable to work today. I'm very unhappy that I'm speaking about this, because it was tragedy for people who designed this experiment, who spent many, many years, tragedy for all people who were expecting results from this, beautiful results from this experiment. But today, it seems that at least for next 5 years, at least, we have no chance to see similar or better device in space. Are there direct ways, in addition to these CMB observations, to investigate the internal gas motions and turbulence inside clusters of galaxies? It seems yes. And main reason why I came here, in addition to this lecture and name of Carl Jansky, is the following. I wish to speak with people about this possibility here. There are hyperfine structure lines of lithium-like and boron-like iron-57. These are iron isotopes with 3 and 5 electrons only, very, very strongly ionized. And they have the lines. And these lines are full equivalent to 21 centimeter line. You know 21 centimeter line, when spin is moving of proton of electron, and we can get the emission of photon. Everybody knows this, and NRAO got beautiful results observing 21 centimeter line in different places in the universe. But there are also these lines, and this iron-57, everybody of us in this room has 2 or 3%, or there is exact value, 2.7% of iron-57 in hemoglobin molecule. Main iron is iron-56, and there is this isotope. Why this isotope is important? Because iron is very even nucleus. There is no spin. Therefore, it is impossible to have this line. Iron-57 has spin, and iron-57 has magnetic momentum. Therefore, there is line, and lithium-like and boron-like ions are really great. Therefore, it is important to try to find these lines. Why it is important? Look here, the temperature. 10 million Kelvin, 100 million Kelvin. And these are different isotopes, not isotopes, ions of iron. Hydrogen-like iron, helium-like iron, lithium-like iron, and this is boron-like iron. It's possible to measure, I think, lithium-like iron and boron-like iron. And this is very important. Here in University of Virginia, several papers were written also about lithium-like iron. Today, we are proposing to look also for boron-like iron line. This is the brightness. Brightness is very, very low. You see this cluster, Able 4059. My student, Dima Datsenko from Latvia, Riga, computed. Temperature is 1.2 keV, and you see of the order of 30 microkelvin brightness in the inner 29 arc seconds of this cluster of galaxy, this lithium line. It is a little weaker than 10 microkelvin brightness. This is another cluster. Temperature of this cluster is higher, 2 keV, and you see lithium-like iron is much brighter than boron-like iron. You can measure temperature, you can do many things. But most important, you can measure the velocities inside. And I know that it's a very difficult experiment, but it is impossible to do today in space, and new experiment in space will, I think that characteristic cost of this experiment will be of the order of $500 million. I'm sure that if people will think this very expensive, maybe $3 million, maybe $5 million, but it's possible to get an array of detectors and to do this problem from ground. It's 2 orders of magnitude cheaper, and this is the same science you can measure properties of very hot plasma. Yes, ALMA. I had conversation in Europe, in ESO, with Peter Shaver, with several other people. They're telling that ALMA will be able to do this. But maybe already today, GBT is able to do here, and you are that center. I told you that there is very strong competition between astronomers in different fields. I told you that people are working to detect clusters of galaxies in the universe at different redshifts. I will show you now what people are trying to do. They are wish to get to measure this also in X-rays, several groups, and the best will be we will have overlapping samples of X-ray, SZ, and optical clusters of galaxies. It's important to have redshift determination, and these lines about which I was speaking, about radio lines, will give you immediately redshift of every cluster if it will be possible to measure. We are proposing now to Russian government, there is support. I can tell you support is coming because Russia has unbelievable income during these years due to very high prices to oil and natural gas. Government is afraid to spend this money because they're afraid of inflation, but at the same time, Russia never had so much free money as now. You know that we are repaying debts and so on. Under these circumstances, it's possible to speak again about new space projects. Therefore, we are trying to do something. And what we are planning to do, we are planning to make the deep sky survey in X-rays, 0.510 keV. This will be more than 1 million AGNs, which we are able to detect. It will be more than 100,000 clusters of galaxies, depending on the model, from 100 to 200,000. Then we will be able to measure acoustic oscillations at several small redshifts. We know from theory physical scale of these wiggles for any model of the universe. And measure at angular scale will give us a way to measure contribution of dark energy to the dynamics of the universe at different redshifts. It will give us the equation of state for dark energy. It is very, very important today. Today we have good data from CMB only for 1 point, redshift 1100. Therefore, we are working very hard today to find what such experiment will give. We already guaranteed by government that there will be Soyuz launcher for this. We are speaking about spacecraft. This is the Yamal spacecraft. It was paid by Gazprom, and 2 spacecrafts are in the sky, and other 5 are in the production line. Therefore, we are working very hard on this, and our dream is to observe clusters which nobody seen before, and to synthesize the skeleton of the universe where the bones will be these clusters of galaxies. This is our dream, and I should conclude my time. I can many other things to speak about, but I wish to tell you that we are really happy because today is the greatest time for astronomers and physicists. We are observing our universe in all spectral bands from radio to X-rays and gamma rays. Every day is bringing us new information about our whole universe, and every day we are discovering something new that was impossible to study in labs. Nobody knows today what is a dark energy or dark matter, but we are certain that dark matter exists. We measure its gravity and contribute several times more than matter density in the universe than usual atoms. The goal is to understand the origin and the fate of our universe. Fate is also important, and why we are living in so comfortable and beautiful environment. Thank you.
Thank you very much, Professor Sunyaev. Questions from anyone? Yes, please.
Can you tell me what to tell my students when they ask what dark energy is and what dark matter is? What's a nice undergraduate description?
Undergraduate description is the following. We know that there is matter, we're just measuring it, which has gravity, which attracts other particles. At the same time, these particles, you know why we know particles which are strongly, you know that there are particles strongly interacting, weakly interacting, and there are particles which are very, very weakly interacting. And these particles are very, very weakly interacting. So that we cannot see, they can go, so you know that neutrinos can go easily through the Earth. Nevertheless, there are so many neutrinos that we are able to detect them in the labs. Plus, cross-section is increasing with energy. These dark matter particles are very cold, cross-section is very low, and they're going, they're here. Many of them are between us and inside us, but we cannot feel them. Today, our goal is to find somewhere the decay of these particles or their annihilation, and we are looking for this. And I am sure sensitivity in gamma rays is increasing so rapidly that we will detect their decay in astronomy from these huge concentrations of matter. 2 days ago, I was giving talk, or 2 days ago in NRAO, I was telling that with integral spacecraft, we are observing huge annihilation of positrons in the central part of our galaxy. 6 degrees of our galaxy are very bright and electron-positron annihilation line. 2 times 10 to the power 43 positrons are annihilating per second. One of the possibilities that they are coming from dark matter. We are looking for everything. I cannot prove. There are other ways to produce these positrons, but we should seriously think about every possibility to detect them. And people are working. But I showed you clusters of galaxies, their gravity, we measure the velocities of the galaxies, and we measure how much matter is in the galaxy, in the gas. It is 30 times less than mass of dark matter, which is keeping clusters together. The same CMB is telling us. Dark matter is simple, but dark energy, it's a question. You understand me? But it is very interesting that we see effects which were not predicted practically. There is lambda term in Einstein equations, maybe you know. Universe is behaving so that something is expands or began to expand, began to accelerate expansion of our universe beginning of redshift 1. And we see this observing distant supernovae. We see this counting clusters of galaxies, and we see this observing these acoustic wiggles. And because it's coming not from one side, not from one experiment, but from 3 experiments, and the result is the same. Not 3 experiments, 3 types of experiments. There are tens of experiments in every group of people who are doing this. But people are very sure that there is something very, very interesting, nature of which we do not understand fully today. There are many hypotheses.
Yes. You showed that lovely zooming in on the Millennium simulation, and I understand there's an awful lot that is kind of correct about those simulations, but there's an element which is, I think, causing problems. The last frame, when you're on the big cluster, has many, many small units in the halo. and those, for the most part, are not really seen in real clusters. I wondered whether you think that that's a
I
significant...
can tell you that, yes, your question, it's absolutely obvious that you are professional. Because, you know, please understand that I will not speak about this and I never will show myself on the talk Millennium Run because it's not my simulations, just. But I am present on many discussions in our institute. Group of Simon White is discussing this very, very seriously. People think that, and you know that there are such objects, people think that there are objects with very small amount of baryons which we practically cannot see. But their gravity we will see in this way. This is one of the ways. Second, we are sure that simulations are correct. Question is, are all conditions which we are including, the whole power spectrum of initial perturbation, is this correct or not? And one of the most important things that we have predictions, people are checking, and they're finding is it where we have real correspondence of observations and simulations, where not. And this is way how theory and simulations will go further. 3 or 5 years ago, nobody was discussing this contradiction. Now people understand because simulations are so good and observations are becoming so good. But I think that simplest explanation is that there are objects also, halos, with very small amount of baryons, and with very small amount of stars, with very small amount of emitting gas. I'm sure that
I'm not a professional.
oh, yes.
The final 2 words were that this is a beautiful universe. And it seems to me that the events that have occurred on the planet in the last month have pointed to our having rather a hostile and irrational universe. We have the hurricanes in the Caribbean and the earthquake over in Islamabad and Kashmir. You show pictures of galaxies coming together, and all I can think of is this colliding matter where things are being destroyed and the universe is being, people, if there were people there, they would be killed. So what's happening? Is it beautiful or is it hostile?
May I tell you that I consider situation even with hurricanes a little in different way. I think that this is nature, and our universe will be, this is again, all these hurricanes are the results of the reality. You understand me? This is the nature of our planet. All this earthquake, huge earthquake in Pakistan, which killed a lot of people just recently, you know, this is because our planet is alive. Continents are moving, all these plates are moving. It's not static. And this is very, very important that science exists and it understands. And all these earthquakes are confirming that really plates are moving. You understand me? And I myself, I believe that such cataclysms, for example, in Himalaya earthquakes, they were practically all time during last maybe billion years, because India came and there is a collision with with Euro-Asian platform. And I read several days ago the list of earthquakes which occurred in the same region, not in this tiny region, but everywhere where Himalayan Hindu Kush chain, where these great mountains are staying. And you know, as Brits came there, as India was colonized, they were writing post factum about huge earthquakes. This earthquake in Pakistan is much weaker than earthquakes which were occurring in 1931, in 1908, in 1871. You can see the list. I think it was published just recently in Economist even. Situation is at that time, nobody was reporting next day about this. Nobody was showing how people are dying. Today, you know, we are reading this next day, or even we see on internet, in television, the same day what occurred in different parts of the planets. If, you know, tsunami in Japan, they were always. There were islands which were, everybody was killed there, you know, but usually people only on local infinity around at 100 kilometers, they knew about this island, but other people never heard. Today, we understand that our globe is very small and we know every day what is occurring there. Obviously, the catastrophes, which I showed you, collisions of the galaxies, energy is many, many orders of magnitude higher. But many things are similar, and it's great that there is science, and we are understanding these things everywhere from the scale of our globe up to universe.
So is it beautiful or is it tragic?
You know, it is tragic for people who are living in this place. But I can tell you that maybe it was so important for us that continents were moving, and you understand yourself that, for example, the role of Gondwana, of changes of climate and so on was unbelievable in changes of our genotype. And I don't believe this tragedy for individuum and tragedy for the whole life on the ground, they are a little different things. You understand me? Therefore, I don't know. It's very difficult to speak when people are dying, to tell such things. At the same time, there is a reality, and we should build houses which will not kill people when there is a quake. You understand me? There are ways, and we are learning how to survive in the universe which is such as we have. Today we cannot change our universe. We even, the worst is that maybe we are changing situation on our planet and accelerating these events which are occurring. Hurricanes are really today more often than they were 20 years ago. But I am sure that maybe 3,000 or 5,000 years ago or 100,000 years ago, situation was even worse. Because it's very interesting to go to any museum in Europe. I am living in Munich now. Beautiful place, you know. Munich, 300 meters of gravity below Munich. There was huge flow of ice from Alps till 10,000 years ago. And whole Germany was like Alaska or Chukotka today. You understand me? And this was not much better than today.
Yes.
What does the cosmic and microwave background tell us about the nature of our physical dimensions?
Oh, a lot of people are now trying to find things which is impossible to explain with our four-dimensional universe. But today from CMB, we do not have any confirmation of this.
I was speaking specifically of our three physical dimensions.
Yes.
That they're either infinite, finite and bounded, or finite.
Oh, you are speaking, now I understood. I can tell you that today the worst situation is the following. When I was of your age, everything was very simple. If we will find that omega amount of the density of the universe exceeds critical, then we are in closed universe, which is infinite, but at the same time, which has finite amount of baryons inside. You understand me? But if it is open, then it is infinite and so on. These were mathematical solutions. Today's situation is much more complicated because people are considering brane world, people are considering other dimensions and so on. People are working, but I can tell you that present-day CMB doesn't give any important information, any clue. We do not have yet, but people are working, and most important thing I told you about why we need sensitivities which will be 4 orders of magnitude higher than present today to measure polarization, because measurement of bipolarization will give us information about most early about process of inflation practically. what's the generation of gravitational waves, so and so on. And then we are very close to next steps in theoretical physics. But it's a very difficult problem today.
Well, in view of the lateness, I'd like to take this opportunity to present this plaque to Professor Sunyaev.